será oferecida pelo professor Roger Jean-Baptiste Wetz, da Universidade de Califórnia, Davis. Ele vai falar sobre Stability of Equilibrium Points. Professor Wetz obteve o seu doutorado na Universidade de Berkeley em 1964, sob orientação de George B. Danzig e do professor Blackwell. Ele é membro das Academias de Ciência da Rússia e da Ucrânia, é ganhador do Prêmio Danzig e é uma das maiores autoridades mundiais em otimização estocástica. Bom, Roger.
Thank you very much, Alfredo. I'm going to speak about stability of equilibrium points in a very general way. This project started a few years ago when we were interested in looking or starting to look at equilibriums in a stochastic, in a random environment. And in order to do that, you have to look at what happens when you have an equilibrium problem and you change the parameters. And that led us to the question of the stability issue of equilibrium points. Let me give some example of equilibrium points. The first equilibrium point, although you may not think in those terms immediately, is looking for the solution of a fixed point. You have a compact set, a continuous compact convex set. You have a continuous mapping G from that set C to another set C. And you have a collection of sets that I will call C nu, which also are compact and convex, of a continuous function for each nu, a continuous function G nu going from C nu to C nu. And the question is the following. Suppose that these approximating sets C nu, G nu, or the combination of pairs C nu, G nu, have fixed points. Does it turn out that actually the fixed point in questions converge to a fixed point of the limit problem, which was the one involving the function G? When is x point, the question is then, when is x bar a fixed point of the problem at hand? And the approach I'm going to use, this is a common approach, is I'm in each case going to define a bivariate function. And this bivariate function will be defined as k on the product of C times C, a collection of bivariate functions k nu defined on the product of C nu times C nu, and I'm then looking at the definition, which is given simply as gx minus x times y. So in a product of gx minus x with y, in the case of the approximating function of g nu x minus x times y, defined on C nu cross C nu. And then the question is, it turns out that you can then show very quickly that x is a fixed point of any one of these problems if and only if x is actually the max inf of the function k. So what type of convergence do I need to impose on the bivariate functions k nu converging to k in order to have convergence of the max inf points? We go to another example. Variational inequalities. They come up in finite dimension, but they come up also in infinite dimension. Most of my talk will be concerned with finite dimension, but the extension to infinite dimension is not necessarily straightforward, but can always be worked out. So in a variation inequality, you have a set C. It's a non-empty set. You have, again, a continuous function G. And you have to find a point U bar, which is such that minus G of U bar belongs to the normal cone to C at the point u bar. And the normal cone is the outward pointing cone in this particular case. The question is the same. You have a series of approximating sets, C nu approaching C, you have a sequence of G nus approaching G, or defined not necessarily on the same sets. The sets change, and the sets change with the definition of G nu. And you get approximating solution to the variational inequality. And the question is, when does it turn out that the limit of the approximating solution is a solution of the variational inequality? And the approach is, again, the same. You define a bivariate function, this time defined as g of u times v minus u on C cross C. And you show that a solution to the variation inequality if and only if the point that you are looking for is the max inf of the bivariate function k. And there's a quick proof, but we don't have the time to really go through it, but it is very straightforward, I assure you. So we have reduced the problem once more to finding the max inf point. And so the question is, you have the approximating bivariate functions defined in terms of the approximating functions g and the approximating sets C nu. And the question is, given that u nu is a max inf point of these approximating sets, what type of convergence do I have to impose on the k nus in order to have the convergence of the max inf points? Another example, and the last one in the introduction, comes from non-cooperative games. You have a collection of players. The payoffs are given as u of a, that is the payoff, that depends on the decision of the player itself, xa, and the decision of all the other players, and that's the notation x minus a, meaning that these are the decision of all the other players. And you have a Nash equilibrium to such a game if it turns out that when you plug in the solution selected by all of the other players and you maximize your payoff function for the player in question, it turns out that the solution is also x bar a. So that would be a Nash equilibrium 1, which actually gives you the optimal solution when you consider that all the other players have selected their optimal solution. And the approach that I'm going to take to look at stability issues and approximating issues is I'm going to define a Nash function. And the Nash function will be defined as, you see, the sum over a of all the utilities, of all the payoffs, with x of a, x minus a, and then minus the sum of all these payoff functions, but this time with the selection of the first variable being ya instead of xa. And you show, very straightforward, that this is a Nash equilibrium if and only if, again, the x bar is the max inf point of the Nash function. And, excuse me. So the Nash functions, the approximating Nash function, of course, are made out of approximating the payoff functions that may be defined on various domains. And the question is once again the same. Do I have convergence of the max inf points? What type of convergence do I have to impose on the Nash functions in order to obtain as cluster point of the approximating solution an equilibrium point of the limit problem? Here are some of the applications of this. It applies to the case in which we are looking at saddle points, and if I have the time, I will certainly get to that when at the end of the lectures, in the case The bivariate functions are Lagrangians or Hamiltonians. Fixed points I spoke about, solution of cooperative games, non-cooperative games fit in this framework. The question of economic equilibrium in the case of Walras, generalized Nash equilibrium points, generalized Nash equilibrium points, the solution of set-valued inclusions in which you, instead of having equalities, you have belongs to a certain set, and in more in partial differential equations, for example, all terms related to the mountain pass theorem. So before I go into the subject itself, let me first start by looking at what happens about questions of stability in an optimization framework. Optimization framework in finite dimension, but the theory once more extends also equally well to infinite dimensional problems. We are going to look at the max of a function f, where f is defined from Rn to the extended reals. And the way an optimization problem is always put in that form is by doing the following. You define f to be equal to your natural objective function, which is f naught on the set of constraint and defined as minus infinity outside. So when you maximize f, you're essentially saying that you want to stay away from minus infinity, which is not a very good maximum value. And C is the set of all the constraints you may have, fi of x less or equal to 0, fi of x equals to 0 for some of the constraints. And all of this is included in the set C, and then you define an extended real valued function. The importance of approaching this is, in this way, is that it defines, in a natural way, some important geometric object associated with this function that we will call the hypograph of the function f. I see g there, but it should be hypo f. So the hypograph consists of all the points which are on the graph of the function and below it. Okay? So the instead of looking at the graph like we usually do in classical analysis, we are going to look at the hypographs. And that is in the case of a maximization problem. And we are led to the notion of hypoconvergence. And I'm looking here in the maximization framework. If I was dealing with a minimization framework, I would be looking at epigraphs, which are the sets determined by the graph and what lies above the function. And what we want is that the notion of convergence, which says that the argmax of the approximating problem is about the same as the argmax of the limit problem. So that's the notion of convergence that we want. Moreover, if we insist, for example, that under small perturbation, continuous perturbations of my function f and the approximating functions f nu, I keep the convergence of the argmax, then I'm naturally led to the notion of hypoconvergence. There's a definition which usually the definition is given for extended real valued functions. Here I'm going to limit myself to the case where the functions are defined on a set and the approximating functions are defined potentially on other sets. And you have a certain definition which requires that you have a lim sup inequality satisfied and you have a lim inf inequality satisfied in the case of sequences. So for every sequence that approaches x nu, which approaches x, I must have that the lim sup of the f nu x nu is less or equal to f of x, and similarly for the lim inf. I'm going to try to bypass this by simply looking at the properties. Namely, what happens is that you essentially look at the set convergence of the hypographs. So you have a hypograph which is the limit one, which is the last one to the right, and you see that the hypographs are approaching, and once you have set convergence of the hypographs, you will say, I have convergence, hypoconvergence of the functions. So now, why are you dealing with the problem in this way? Is because you want to handle constraints and objectives in one sweep. You don't want to have necessarily something which happens, you want the conditions on the constraints, conditions of the objective. You can eventually get to that point, but you want to essentially have an idea of an approximating problem. And the properties that you have are, before I get to the properties, maybe I want to compare it to some other notions of convergence you may be more familiar with. Hyperconvergence and point-wide convergence don't match. Neither implies the other. Okay? But that is not very important, because point-wide convergence of such functions doesn't guarantee the convergence of the argmins. Uniform convergence is much stronger than hyperconvergence, but on the other hand, in the setting in which you have the domain of the functions changing, you would never have hyperconvergence except in unusual cases. The important property is the following. If you have hyperconvergence, and I see that there's a little e left there, but actually it should be hyperconvergence, then the argmax, if you look at the sequence of points which belong to the argmax, and these points do converge to something, then this something is also a maximizer of the limit function f. Another property, which is related, it says, take any point which is a maximizer of f, then you can find approximate maximizers of the approximating functions f nu, which will converge to that point. Final property is that there's a whole topology. That means it's not just the notion of hyperconvergence comes with a whole topology associated with it, and you can actually metrize it. You can define the notion of a distance between hypergraphs, and in fact you have hyperconvergence only if you have convergence with respect to this distance. For those of you who may be working in partial differential equations, this would be related to gamma convergence, which is... Now I'm going to impose something a little bit stronger than in the application. I'm going to need something stronger. Namely, I'm going to need the convergence of the maximum values. In order to achieve that, I'm going to define the notion of hyperconvergence tightly. Tight hyperconvergence. Now, one way to do that is to say, well, the domains that I'm looking at are all contained in a compact set. But that is, in application, this is not very good assumption. So the way you replace that is you say, well, I look for an epsilon. And for that particular epsilon, which is larger than 0, I still have hyperconvergence like the one which I have defined before. And I can find a compact set such that if I look at the supremum of that function over this compact set, it is no further away from the true supremum by epsilon. So that is tightness that we will impose on hyperconvergence. And with that, we have the following general term. If we have hyperconvergence tightly, then, and the sup happens to be finite valued, then the sups converge, or the maximums, if they happen to be a maximums, converge. And in addition to that, I have the property which I had before, namely the convergence in the solutions in the way I have described earlier, namely the cluster of any collection of solutions of the approximating problem is a solution to the limit problem. Okay, so that is the case for one variable, univariate functions. Now we're going to look at bivariate functions. And what we are looking for is the convergence of the max-inf points. You remember that in the case of the unit variable, I was mostly concerned with a type of convergence that will guarantee the convergence of the argmax. Here I'm going to be concerned with the max-inf points. Namely, what convergence do I have to come up with to guarantee the convergence of the max-inf points? And what do I mean by a maximum point? I mean that it's the x which is going to maximize the infimum with respect to y of the function k of xy. Well, let me try to do as well as I can with the definition. Speaking about functions of two variables is always much more complicated than functions of one variable. There's no geometric object that goes really easily with it. So here I'm going to have a function. My approximating functions are going to be defined on sets C nu cross D nu. My limit function will be on C cross D, and I'm interested that what happens for every point xy, but I've selected to pick the point which happens to be a corner of one of them. The first part of the definition says, whatever be the sequence x nu converges to C nu, I will be able to find a sequence y nu converging to y, with the y nu belonging to D nu and y belonging to D, such that the lim sup inequality which I had before is satisfied. Namely, the lim sup of the k nu x nu is less or equal to k of xy. And there's a condition what happens on the boundary if I don't get, if that sequence x nu doesn't converge to a point in C, I have also to say what happens. So in this case, I have a particular way to counteract, if you like, the choice of the sequence x nu going to x. I have a way to choose my sequence y nu going to y. On the other hand, I'm going to look at the second part of the definition, and here it's a much stricter type of condition. It says, there exists a way to select a sequence x nu, and I do this a priori, which is such that whatever be the sequence y nu that I choose, I still have the lim inf inequality satisfied. Namely, the lim inf of k nu of x nu y nu is larger or equal to k of xy for every y which belongs to D. Now I've circled there exists because I'm going to, if I ever get to saddle points, we're going to see the difference with that type of a condition. And with this class of conditions, I have something similar, if you remember the lim sup lim inf inequality in the univariate case, but now I have also to play with the second sequence in order to do that. Well, the elementary properties, does this make sense? Is this actually a convergence that is consistent with everything which I have done before? And I remind you, I'm interested in getting maximum point. Well, if I take the definition, I reduce it to the univariate case, I'm back to the univariate convergence, namely epiconvergence and hyperconvergence, depending if I have a function which doesn't depend on the other variable. But this time, if you are familiar with gamma, it's not a gamma convergence. Okay? And of course, what would happen in infinite dimension is I would put different topologies in order to make the applications. I have a similarly definition which I need of tightly, which says, well, the second condition, which I had on the lower part of the previous transparency, I will reinforce it a little bit. It will say that when I take the infimum and I look at the infimum of that function with respect to the second variable, then the infimum is the same as if I restricted the domain to a compact set up to epsilon. Okay. So the theorem now says that if I have lopsided convergence and x bar is a cluster point of the maximum points, then x bar is actually a maximum point of the limit problem. Okay? So this is an important property which allows me to conclude that I have convergence of the maximum points if I have lopsided convergence. The word lopsided, by the way, comes from the fact that it is one-sided, that it applies to the Maxim's case. It doesn't apply to the min-sup case. Okay, so you cannot interchange. You have it only on one side. That's why the conversion is called lopsided. The proof actually is, at least the idea of the proof is relatively simple. You define the marginal or introjections of the bivariate functions k, namely, you look at it simply as a function of x, and you show that as long as the domains of these functions are non-empty, that means that they are defined on non-empty sets, you have hyperconvergence. Then apply the result on hyperconvergence, for which you have convergence of the argmax, and you are home. Now, the second issue which may come up is one in which you say, well, when do I have existence? And one important tool which came up in this area was the use of so-called Kiefan's inequality. Dates back to the 70s, but is very useful in the applications. Kiefan proved the following. Suppose that you have a bivariate function, and it happens to be upper semi-continuous in the first variable and convex in the second. And it happens to be defined on the product of two compact sets, C cross C. Then the Maxim's points, there exists a Maxim's point. You can show that that is essentially equivalent to a fixed point theorem, but it has advantages here because we are looking in the class of bivariate functions. Moreover, if it turns out that that function happens to be non-negative on the diagonal, then if I look at the function, at the marginal function at that point, at a point at which I have achieved a Maxim's point. So if x bar happens to be a Maxim's point, then I will have non-negativity for that function all the way through. Now, what I will call a generalized Kiefan function is one where we don't insist on the compactness of the sets in question. And it's very natural now to generalize the notion of Kiefan to a more general class of functions, namely those which are not defined on compact domains, but are defined over arbitrary domains. But you can identify a class of Kiefan functions that will converge to that one. And so we obtain the notion of a generalized Kiefan function, not defined on compact domains. And let's suppose that we have such a collection of Kiefan functions that converge lopsided tightly to one of those functions not defined necessarily on compact domains. So we go from Kiefan to generalized Kiefan. And suppose that x bar is a cluster point of the cluster point of the Maxim's point of the approximating functions. Then x bar is actually also a Maxim's point of the limit function, and you have the non-negativity property for the marginal function at that point, x bar. What is interesting to observe is that if you look for classes of functions that are closed under various convergences, then Kiefan functions are closed under lopsided convergence. I did not mention that, but if you look at upper semi-continuous functions, they are closed under hyperconvergence. And although we haven't spoken about them, saddle functions are closed under hyper-epiconvergence. So let's apply it now. Let's go back to our Brouwer fixed point theorem. We have a compact set. We have a continuous function. And x bar is then, there exists then, we know a fixed point. We define our bivariate function. We look at the properties of our bivariate function. It happens to be a Kiefan function defined on a compact set. So Kiefan inequality applies. because that function is upper semi-continuous in the first variable, it's convex in the second, and it's non-negative on the diagonal. So we have a max-inf point of k, and from that max-inf point, we can conclude that that point is a fixed point of the function g. Now we look at the approximating or stability issue. We're going to move the sets, we're going to move the functions, and we're going to ask that they converge in a certain way. For the sets, we apply set convergence, so you have the convergence. If you're not familiar with the convergence of sets, there's something called the Hausdorff metric, but that is restricted to compact set. In general, notions of convergence of sets go back to Pain-Levé. This is Pain-Levé's notion of convergence. So C nu goes to C, which happens to be compact in this. If C happens to be compact, then the approaching set in the convex case also eventually get to be compact. We insist that the convergence of the approximating functions g nu to g be continuous. What that means is that for you don't have just pointwise convergence, but for whatever be the sequence x nu approaching x, the g nu x nu approach g of x. In that case, the corresponding bivariate functions lopside converge, and in fact they lopside converge tightly. Each one of the approximating problem has a fixed point, and if these fixed points have a cluster point, which they necessarily do in this case, then that limit point is actually a fixed point. And I should, by the way, say that this fixed point result applies not just to Brouwer fixed points, but to Kakutani, Schroeder, and so on. And of course, given that we also allow the possibility of our bivariate functions to be defined on non-compact sets, we have an extension of a fixed point here, a very natural extension of a fixed point to situations where the set C, which we are interested in, is not necessarily compact, but is just convex. I'm going to skip this because, but I'm going to mention what the problem is. You have an inclusion is essentially a relationship in which, if you look at the second line, you have a set-valued mapping, and you want to have 0 belonging to this set-valued mapping. And the question is, can you apply the theory to this particular case and obtain convergence of the solution? And the way you deal with that, because you insist that the set-valued mappings be convex-valued, you deal to this through the support function, and you arrive at key-fan functions, which in turn give you the convergence of the solutions to inclusions, and in particular application is to differential inclusions. In variation inequalities, if you remember, we had a compact convex set C. We have a continuous mapping G from C to Rn, and we have to find a U bar which belongs to C such that minus G of U bar belongs to the normal cone to C at the point U bar. And the normal cone is if you have a set C at U bar, it's the cone which points outward. If you don't necessarily have differentiability, if you have a smooth boundary, which can be described by a manifold, you would have the tangent. The tangent half space. Okay, so now what you do is you define again a a bivariate function k of u, just like I said in the beginning of my lecture, g of u of v minus u. This is defined on a domain C. This happens to be a key-fan function, which happens to be non-negative on the diagonal. And so what you have to do to solve the variation inequality is actually find the point u bar, which is the max-inf point of that particular bivariate function k. In convergence, you have the same property. You ask for set convergence for the domains, C nu going to C. You ask for continuous convergence for the approximating function G nu going to G. And again, I remind that this implies that for every sequence approaching x, we have that G of x nu approaches G of x. You define your bivariate function k. From that, you observe that it is a key-fan function. And it turns out that that collection under these conditions will converge lopsided tightly. Any cluster point of the solution of the approximating variation inequality is a solution of the variation inequality. And these are sufficient conditions, not necessarily the best one. And again, you can extend this to the non-compact case, as I indicated before. Nash equilibrium, you do the same thing. Now that you know the pattern, it's very easy to essentially use it in various situations. You have the notion of a Nash equilibrium of a non-cooperative game. We define the Nash function. This Nash function is the one which is defined on line 3, namely the sum over all agents of the payoffs, where the first variable is xa, and the second variable is the decision of all the other players, minus the summation over A of the payoffs of all the players, but this time where we allow a change in the decision of the first player, but we keep the second players fixed at x minus A, all the other players fixed. That function, if we have upper semi-continuity, which is the usual property in non-cooperative games, we have upper semi-continuity of the function UA, we have lower semi-continuity with respect to the second variable, and we have concavity with respect to the first variable. Then n, the function n, is a key-fan function, which is non-negative on the diagonal. If it turns out that we have continuous, and actually something weaker applies, hyperconvergence of the payoff functions, if we have that the domains converge to a limit compact set, then we have lopsided convergence tightly, and we have convergence of the Nash equilibrium points for non-equilibrium. In the case of Walras equilibrium points, for some of you this may not be familiar, but let me define what a Walras equilibrium point is. You have a collection of agents in an economy. Each one has a utility function, UA, which depends on the consumption, which is denoted by XA here. You have a budgetary constraint, which says that given your endowments EA and the prices that are being paid for these endowments, your consumption, the total consumption that you make, has to be less or equal than your wealth, calculating use these prices P. SP dA is then the optimal solution of such a problem, dA of P. It depends on P. We look at the excess supply as a difference between the initial endowments and the demand that was created by each agent solving individually its maximization problem. And the question boils down to the following: can you find a price system and without loss of generality you can restrict yourself to the unit simplex such that actually there is excess supply or supply is equal to 0 depending on the way you are. You set up again a certain natural function connected with this particular problem, which depends on P and Q, which is the inner product of Q times S of P. It's, the function is clearly convex in Q because it's linear. It's continuous it's actually continuous in P if you have unique solutions to the individual agent problems, assuming strict concavity, for example. And the question is, can you find, and you show that you will have an equilibrium point, a price equilibrium point in this market if P bar turns out to be a Maxim's point of the Walrasian. And under certain conditions, which if you are interested I can go into, namely if the endowments are inside the set of survival for all the agents, there's a global compactness conditions, you obtain the convergence lopsided of the Walrasian. But this has led to numerical schemes. For example, in the case of numerical schemes, two of my ex-students got together and decided that they would actually compute, find methods for computing these equilibrium points. Now, there had been work in this area by Scarf, Eves, Saigal, and others using piecewise linear homotopy type methods where they could solve equilibrium points for this class of problems involving 4 agents and maybe 5 products. So, but realizing that actually what we look for is a Maxim's point and falls naturally in the area of optimization, they decided that maybe they could use techniques which were related in one way or another to those that one used in augmented Lagrangian. So they set up an augmented Walrasian, and the augmented Walrasian is defined, and that augmented Walrasian, when you take the coefficient r sufficiently large, happens to be convex concave. And for these class of problems, namely saddle point problems in which you have convex concave functions, it is very good. And you can iterate, and I won't go through that. The iterations are easy to really easy to perform. And in less than 2 seconds, they solved their first experiment. They involved 10 agents, 150 goods, and they solved it in less than 2 seconds on a laptop. So there was really a jump which showed that optimization techniques are really very powerful in this area and can surpass those which are standard for equilibrium point. So to summarize very quickly, what I've done is not just spoken about convergence, but what I've done is something beyond that. Namely, I've said, look at all the fixed point problems, all the variation inequality problems, all the Nash equilibrium problems. So you can always formulate them as Maxim's points. And for Maxim's points, you can construct effective algorithms that are numerically very good. The demand functions, they use particular saddle functions. Let me now say a few words to terminate about saddle points. Now, in the case of Lagrangians and Hamiltonians, but I won't be able to speak about the Hamiltonians, you start off with a certain problem having maximization of a function f naught subject to constraints. Some of them are inequalities, some of them may be equalities. You usually construct from there a certain Lagrangian, and the Lagrangian in this case, in particular, is simply you associate with the constraints multipliers that I called yi, that need to be non-negative for those which have inequalities in them and can be arbitrary for those having equalities. So you have a Lagrangian function, and if the inequality is not satisfied, you extend it to the whole space by saying it's minus infinity. And if the functions f naught happens to be concave, the functions fi involved in inequalities are convex, fi equals 0 happen to be affine, then you are dealing with a concave convex problem. And I stay in the Maxim framework, as you will see, because I will be maximizing with respect to x and minimizing with respect to y. But of course, and it's very important to make this distinction because the theory is not symmetric necessarily. Now, in this case, if we are interested in saddle functions, we would be interested in approximating the saddle points. And in the 90s, with Eddie Attouche of Université de Montpellier, we did a lot of work about convergence of saddle functions. We came up with a certain definition. I'm not going to be explicit about it, but one of the difficulties we had is when we looked at the so-called, we called the convergence the hypo-epi convergence, or epi-hypo, depending on if you were looking at the min subpoint instead of a max-inf point. So a hypo-epi convergence turned out the topology that we generated to this notion of convergence did not turn out to be a Hausdorff topology. And one of the problems is that we did not make the distinction between a max-inf point and a min sub framework. So we did have a very nice example of some exotic topology, but when we then went to some applications, we were getting into problems. I'm going to compare this definition with that I gave for lopsided convergence. I start with the same framework, and the first definition is the same. For every possible converging sequence x nu in the C nus, I can find y nus which will enforce the lim sup inequality, namely the lim sup of the approximating values is less or equal to the limit value. And there's a special condition when the convergence of x nu to an x which doesn't happen to be in the set C. So that's exactly like we had in the lopsided convergence. But of course, what we expect for saddle point is that things would be symmetric. So this time, if you remember, I started last time, I think, the lopsided insisted that we start with a notion that we have a particular sequence x nu for which whatever be the sequence y nu. Here, we say, well, for every sequence y nu, we can actually find a sequence x nu such that the lim-inf inequality is satisfied. And here we have a difference with lopsided convergence. We see the difference between the two definitions, which gives us, in some way, immediately the idea that lopsided is really one-sided in its approach. The elementary properties is, again, now we are concerned with approximating saddle points. We still have that if one of the two variables don't appear, we are consistent with the univariate gate. But one important thing is, those of you who may be familiar with epiconvergence and hyperconvergence, it is not a combination of these two notions. It doesn't demand that we epiconverge with respect to the minimizing variable and that we hyperconverge with respect to the maximizing variable. That would be too strong a condition and very important. And again, it's not a gamma convergence. And again, we have done applications in different topologies once you are in infinite dimensional spaces. The major result says the following: if you have hypoepiconvergence of the saddle functions, and x nu y nu is a saddle point of the approximating saddle functions, then any cluster point of that sequence will be a saddle point of the limit function. And the applications, I won't detail them, but they give applications to cooperative games, zero-sum games, convergence of the solution of zero-sum games. You get joint conversions of the solutions of dual convex problems, namely in convex optimization you have a primal problem, a dual problem, you have joint convergence of this. There are applications in mechanics that would take a long time. And as you expect, lopsided convergence does imply hypoepiconvergence. So it's a stronger notion, but not conversely. And there's an example there, but in this example, we have a function which is defined as -1 on a particular product of two sets, and which is 0 just at the corner point. And we're looking at the limit of that function when we see that also the limit function is -1 everywhere except at the corner point. And you can see that you get hypoepiconvergence, but you don't get lopsided convergence. Namely, you cannot find, and that's the difference between the two conditions, you cannot find a particular sequence x nu going to 0 such that whatever be the sequence y nu, you have the convergence that is appropriate. However, there's some relationship that you can show, namely if you have hypoepiconvergence and your function happen to be convex concave, then you actually get also the stronger version, namely lopsided convergence. And when you check that, the first condition doesn't need to be checking because in the two definitions, these conditions are the same. For the second conditions, you show that you can make every point in the limit function to be a saddle point of a modified function, namely one in which you change the original L and L nus by adding linear terms that are determined by elements of the gradient or subgradient of the limit functions. And in that case, all of these approximating points are then saddle points, and the saddle points we know in the case of hypoepiconvergence do converge, and that you get the sequence. I think I will stop here, and I've given enough examples to convince you, I think, that for equilibrium problems, you really should look at them as Max-Inf points. You have all the stability theory that I have been detailing at this point, but you also have the fact that numerically there's a much better chance to solve such problems by looking at the problem in that form. Thank you very much.
Any questions? Well, thank you, Roger.
Thank you. Okay.